Welcome to Jupyter for First Timers. The goal of this video is to show you how to get started in Jupyter Notebook if you have never seen it before. Jupyter is a wonderful programming documentation environment where you can develop and run code, display the results, and discuss both the setup and the results of your work. So think of it as an electronic lab report or scientific report that you are putting together that has your code and results built in. It's very popular among scientific research communities, especially in physics, astronomy, and by incorporating it into your physics class, your physics instructor is trying to help prepare you for those professional environments. I'm going to start this video assuming that you have been able to log on to Jupyter. That's going to vary based on your system. For my students at University of North Florida, I have included step-by-step instructions of how to get to this point on our Canvas page. Hopefully you have completed those. If not, pause this video, go follow those instructions, and then pick it back up here. Once you have Jupyter open, you're going to need to find a notebook file to work with. Your instructor probably has a favored method of you getting those files. You might download them from your LMS. You might get them from scratch. They might email them to you. For my students in modern physics, you're going to get your assignment files for the class using a command called get. So the first thing we're going to do, and you can just follow along on your own screen once you're logged in, I'm going to click on New here. I've got a few options. We're going to be working in Python later. That's mostly what we'll use Jupyter for. But for right now, I want you to go down to Terminal. This is going to open a command line terminal. It uses some Linux commands. You don't have to learn Linux in order to use Jupyter, but it can help you get some behind-the-scenes stuff. In order to grab the assignments for my class, you're going to open the terminal here. And you're going to enter this command. I'm actually going to paste it in using Control-Shift-V. So Control-V doesn't do paste in Linux. Control-Shift-V does. You're going to type in get. That means literally I want you to go get something off the internet. There's a file somewhere on the internet that I want to get. Get is the name of the site where it's hosted. It's kind of a play on words. You're going to say clone because you want to create a copy of the file that I have. You're not looking to take it from me. You're not looking to edit it yet. You're just looking to clone it into your own server. Then you type in this URL. I will have that URL available in the description below. If you're in my class, you also have it in Canvas. If you're not in my class, you're welcome to clone these assignments and try them out yourself. What this is going to do, it's going to look for my repository over on github.com/letscodephysics, and it's going to look for my repository called modernphysics.git. Once you type that out, or copy and paste it, if you want to be a little bit faster and not mess up a letter somewhere, you just press enter. It's going to spit out some text at you. As long as it doesn't say error or warning, then everything went fine. You notice at the end it says unpacking objects 100%. That means it's done. I can now exit this. You don't ever have to go back into this terminal again if you don't want to. And you notice it gives me a new folder called Modern Physics. And you should have that now. If this is your first time in a Jupyter server, that will probably be the only folder that you have on your server. This folder navigation works the same way it does in your operating system. There are folders that contain files, and then there are the files themselves. Primarily, the files we're going to be interested in are these .ipynb files. That stands for IPython Notebook files. That's what we're going to be interested in. So click on this Modern Physics here, and you'll see all 12 assignments for my Modern Physics class. So for my class, when it comes time to do each of these assignments, you just click on the assignment that you need to complete, and it will open it in a new tab. The way I thought I might give you a walkthrough of Jupyter would be to complete my own assignment number 1. All right, so you get to learn Jupyter and you get to see what Dr. Lane expects in assignment number 1. So what'll happen when I click on this, it's formatted like a hyperlink. It's going to open it in a new tab, and it's going to open the Jupyter Notebook environment here. And then you see in the first paragraph, I give you a little bit of an introduction, and I tell you what you'll be able to do at the end of this assignment. You'll be able to edit, save, and submit a Jupyter Notebook. You'll be able to document your mathematical work using LaTeX. We'll learn a little bit about LaTeX math formatting today. You'll learn how to read a code, modify an existing Python code, add to an existing Python code, read and interpret a code's error messages, fix a code based on its error messages, repeat a set of code with a loop, and graph numerical data, all in this first assignment. So my assignments are divided into steps. Each step begins in a new cell. If you click inside this text, you'll see it gets highlighted. This is a single cell inside Jupyter Notebook. Jupyter Notebook basically contains two types of cells. There's Markdown cells and there's code cells. This one is a Markdown cell, which means it's text presented to the reader that has some formatting options. If you double click on it, you'll see what the Markdown code looks like. Markdown is a way of formatting your text easily on the internet without having a lot of buttons to have to worry about. If you've done a lot of posting on Reddit or in Discord, they use a lot of the same Markdown conventions that Jupyter Notebook does. For example, if you want to give a heading, which you do a lot of times, you use these pound signs to indicate what level of heading. So 1 is the first heading, 2 is the second heading, 3 for the third heading, etc. When you want to make something bold, you just put double asterisks around it, right? So you just do asterisk on one side, asterisk on the other. And then you can also make things italics. I don't see any italics in here, so let's give an example here. If I put just single asterisk around something, you see it becomes italicized. What you'll notice is that it's kind of giving me a preview of what the formatting is. Here it's giving me bold, here it's giving me italics. It hasn't exactly formatted it yet until I click on Run up here. So when you're finished with a cell, you can click on Run, and it will format that for you. And it went down a cell, which is okay. I'll come back up here. And so there it gives me the nice, neat formatting. So the formatted part is for the person who is reading it. So I've made some changes to my notebook now. It tells me that I have unsaved changes, so I need to click on File, and then Save and Checkpoint. That's going to both commit the changes to the document, and it's going to create a backup checkpoint just in case I need to go back and change something. Another thing I need to do is I need to change the title. So if I come up here and double click on the assignment title, I get this little window to give my notebook a new name. Since you'll be submitting this to your instructor, the instructor needs to be able to tell your assignment apart from your classmates. So you need to rename this to include your name. So I might call this Assignment 01 from Ryan Lane. And that's it. That's all I have to do to rename it. So just rename it, include your name. If you want to adopt a different, if you want to say Brian Lane Assignment 1, whatever order you want to do is fine, just as long as I can tell that it's from you so that I can award you your points appropriately. What I'm asking you to do in this step is to tell me about your favorite physics concept from a class you have taken before. And I'm asking you to just replace the text here in the square brackets. So let's see. My favorite topic in physics is connecting resistors in parallel. It boggles my mind that we can add in quotation marks, resistors together and end up with less resistance than we started with! Exclamation mark. So I write a paragraph there. I maybe write another sentence or two just describing my history with the concept of resistors in parallel. I press Control Enter, and there it's got my changes there. And I can go up and click Save again. I can also just click on the Save icon there. Scrolling down to Step 2, Jupyter Notebook allows you to format mathematics using the LaTeX typesetting language. The way LaTeX works, we'll double click to go inside. Whenever you want to make something look mathy, you put it inside dollar signs. So I put $1 over here. I put another dollar sign over here. And in the middle, I put in whatever math I want to format as. So for example, if I want to put in this quadratic function here, I can say f of x equals x caret 2 is going to give me x squared. Watch what happens when I press Control Enter to run this. Notice it gives me x with a superscript 2. So that caret will give you a superscript. If you want a subscript, so if I want x sub 2, like I have an x1, x2, x3, etc., then you just use an underscore. You can even get fractions. So if you input /frac, this is I believe that's the forward slash. It's the one that goes nearest your enter key. then you can get a fraction. You put the numerator in one set of curly braces, and you put the denominator in another set of curly braces. Press Control Enter to run. Lo and behold, I get y over x as a nice, neat fraction. LaTeX knows all of the math symbols you could ever possibly need. And if it doesn't, then you find a package where it does have those things. For example, if you need an integral, you say /int. It will give you the nice integral cello-s thing. If you need Greek letters, you can type in /delta for a lowercase delta. What if you need an uppercase delta? Uppercase delta. It's great. It knows all the Greek alphabets. It knows approximately. It knows less than or equal to. It knows plus or minus. All those things that you struggle with to create in a word processor that shall remain nameless. LaTeX you can just do with a simple slash and a command. What I'm asking you to do here in the space below, this is the first time you're asked to write something in here. I'm asking you to use LaTeX to format one equation based on the favorite physics concept that you described in step 1. I'm going to select this and delete it because that's where I'm going to add my answer. And let's see, I shared with the instructor that my favorite physics topic was resistors in parallel. So what I'm going to do is write out the equation for the equivalent resistance for resistors in parallel. So I need to think about this. This is going into LaTeX, so I'm going to start with a $sign. I know I'm going to end with a $sign, so I'm going to go ahead and add one over here, a few spaces over, just so I have enough space to work in there. So let's see. The equivalent resistance, if this is the equation for equivalent resistance, so that's going to be R underscore EQ. Right? We label it REQ for R equivalent, or RTOT for R total. It's going to have an underscore because it needs a subscript, so underscore goes under the variable. You can kind of think of it that way. Equals, well, let's see, the way I do this is 1 over R underscore 1 plus 1 over R underscore 2 plus 1 over R underscore 3. Oh, yeah, this can be an infinite number, so I'm going to say plus ... All right. Oh, right. I am supposed to take all of those and then raise the sum to the -1 power. So let's put some parentheses around this. Parentheses there. And then I need to raise that whole thing to the -1 power. You notice I'm using these curly braces to group together stuff that needs to go in the superscript or subscript together, because otherwise LaTeX will just use the first character that comes its way and then ignore and then put the rest in normal text. All right, let's run this and see if it looks like the way it looked in my intro physics textbook. Okay, cool. I have answered the question. I have given the equation for the equivalent resistance for resistors in parallel. It's not quite all that pretty. There's some work I could do to pretty it up. So for example, I've got this one slash thing going on. I could make those a fraction, right? So if I wanted to make this prettier, I've technically completed this part of the assignment, but if I wanted to make this prettier, I could do slash frac and then close up my numerator, close up my denominator. You notice I don't need that slash anymore. It's going to automatically put in the horizontal line. Curly brace here, curly brace, curly brace. You notice I've got nested curly braces here, right? I've got one opening here, I've got one opening here, and then close, close. Just count them like you do on a calculator, or graphing calculator, and make sure that you close all the ones that you open. Do the same thing over here. 1 over R3. All right, let's see if that looks any better. Oops, what did I do wrong there? Oh, I didn't put in slash frac. So if it doesn't look like the way you intended, you just go back and see what's missing, right? All right, cool. That looks a little bit better. Those parentheses look funny, right? Because I've got this fraction here. Parentheses are supposed to get bigger with the things inside them, right? This is where you do a little bit of Googling on LaTeX. Anytime you don't know how to do something in LaTeX, like make parentheses bigger, you just Google LaTeX make parentheses bigger. Real talk for a second. When you Google for help with LaTeX, LaTeX, just be careful with what you click on, okay? So you Google and find out that the way you do this is putting in the slash left command in front of the left parentheses and the slash right command in front of the right parentheses. That just means you've got a set of stuff that you want to be bracketed on the left and on the right with. So when you run this, Lo and behold, it makes your parentheses much, much prettier. Hooray. So now I've completed step 2, and it's nice and pretty. Step 3, now that you've practiced communicating about physics, let's generate some physics data using Python code. Let's suppose you wanted to model an electron moving in a circle. You probably remember that you can model something moving in a circle with a cosine function of time and a sine function of time. Now, I'm missing units on the time there because I need to have an omega in there, but Python doesn't know what units are, so we're just going to keep it simple for now. We'll worry about units in future assignments. What I'm asking you to do here is look at a code cell and to describe for me, so you notice I'm asking you to do a description here. I'm asking you to read through the code and then describe what you think each line is going to do. So when I look at a Python code, what I'm looking at is a set of instructions that the computer is going to read line by line and is going to execute one line at a time. It's not doing all the lines at once. It's not jumping around. It's going line 1, line 2, line 3, etc. Speaking of line 1, 2, and 3, one of the things you can change here, if you click on View, you can toggle line numbers, and that'll give you a line number on the code cell there. That's really useful because sometimes you run into an issue and it'll tell you that there's an error in a certain line number, or you're communicating with your instructor and they say, oh, the mistake is in line 17. You use that label to see where line 17 is. So when I read this, what I see, the first thing is from PyLab import star. That's just a library import. That's so that the computer knows what cosine and sine are. It doesn't know those by default, but cosine and sine functions are stored inside the PyLab library, Python laboratory, and it's just importing all those functions there that we might need. And I keep going down, line 3, I see t equals 1. It's pretty self-explanatory. It's saying take the number 1 and store it inside the variable t, right? It's kind of like saving a file, right? You write up a document, you need to save it under a file name. This t, this variable label, is like a file name where you're saving 1. Here, you're doing something just a little bit more complicated. You're saying take the cosine of t, right? It has 1 stored as t. I don't have to put in 1, I just put in t because it already has 1 stored as t. You're going to take that number, store it in x. Then over here, you're going to take the sine of t, you're going to take that number, store it in y. You come down here to line 7, it's asking the computer to print x comma y. That means it's going to show you x and y on the screen. I can click the run button over here, and lo and behold, I get the cosine of 1 and the sine of 1. You can check that in your graphing calculator or on Google. You can also play around with this number, right? So I could change this to a 2, and when I run it this time, I'll get the cosine of 2 and the sine of 2. Say, gosh, those are weird looking numbers. Can't we try one we know the answer to? Sure, let's try pi. Yeah, PyLab knows what pi is. You don't ever have to type pi out again. You can just say pi there. Run this cell. Cosine of t is equal to -1. Sorry, I had to remember where pi is on the unit circle there. And then sine of t is random digits times 10 to the -16, right? So the computer is going to have a hard time getting things down to exactly 0. There's always going to be a little bit of rounding garbage at the end. Whenever you've got a number that small compared to a regular size number here, this is basically 0, right? We the humans know to round that to 0, even though the computer does not know that. And so then you'll put in your description there to tell me about what's going on in that code. I'm not asking you to edit that code. I'm just asking you to read it and tell me what it does. Then I'm asking you to run the code. I actually got ahead of the game there, excuse me, by clicking inside, pressing Control-Enter, and describe to me what happens. Step 4, now it's time for you to modify a piece of code. This is the same as the piece above there. Now you're going to change the value of t and run the code again. Repeat it a few times, confirms that it gives you the correct results. We already tried this, but let's try one more value. Let's try 2 times pi, just to make sure this thing is working correctly. 2 pi has a cosine of 1, a sine of 0, and just for completeness, let's try going to the top of the unit circle, pi over 2, and I get a 0 and a 1. Hooray, it worked out. Do always look for these e negative something at the end because it's going to default to putting numbers in scientific notation, so just keep an eye out for those. Step 5. Let's suppose you now wanted to extend this code to model the motion in 3 dimensions. Tracking motion in the z direction. Starting with the code cell below, add a line of code to calculate z using a power law. So what we're going to do, we need to add a line of code. So we're going to come in here. We're going to press enter to get a new line. And then we're going to type in this power law, z equals t to the p power. So z equals t, double asterisk p. The double asterisk in Python is their way of saying to the power of. We would, in your calculator, probably use a caret, I'm guessing. Unfortunately, the caret is reserved in Python for another function, and so we have to use the double asterisk. You will get used to it eventually, don't worry. Just for now, keep in mind that it's a double asterisk. If you use the caret, it will more than likely give you an error message. So if you see an error message about the caret, just go back and change it to a double asterisk. Let's see. Oh yeah, and then replace p with the number of your choice. Right, because I haven't told it what p is. It's gonna get angry at me if I don't tell it what p is. Why don't we make that square? It can be whatever number you want. I'm also asking you to think about where the calculation of z should go based on how the computer will read the code. Should it go before the t equals 1 or after? Well, let's see what happens if we run it with it after. Let's add in a comma z to the print command. Print command is pretty great. The print command is how you get Python to tell you what it's thinking. You can put print in any set of variables that you want, just separate them by commas, and it will spit those out for you. So if I click this run here, it gives me my answers. It gives me cosine of t, sine of t, and t squared. And you notice I have to place the z here after the t equals 1, because otherwise Python's not going to know what t is, right? It's like when somebody comes up to you and starts using a word that you've never heard before, that you've never seen in the dictionary. Right? You're a college student. That happens to you every day. It happens to me every day. You know, if you use a variable that Python doesn't know what it is, it's going to give you an error. It's going to ask you what's going on here. Step 6. Speaking of which, no one types up code correctly the first time, myself included. And researchers like yourself spend much of their time, 99% of their time, finding mistakes. Here, let me pause for a second. The beautiful thing about scientific programming, you can make as many mistakes as you want. You can get this assignment wrong as many times as you want. You only have to get it right once. And once you get it right, you save it, you send it off, and you're done. One of the ways you can find and fix a mistake in a code is by reading the error messages. This is really important to learn to read error messages from a code. The code below has a mistake. I've deliberately made a mistake in the code here and produces an error message. In the space below, describe what the error message is, telling you how you can fix it. It's already displayed here because I have it saved in the document, but basically when I run this, it's going to think for a second and then it's going to give me this error. What I do is read this error like it's a piece of feedback. It's the computer giving me feedback on something I need to do differently. Name error. I'm not exactly sure what that means, so I'm just going to keep reading. Traceback, most recent call last. The computer will give you that error, that message on every error you get. I'm still not entirely sure what it means. There's some garbage here. Basically, if it looks like gobbledygook, just ignore it. It's the computer giving you some kind of code that you might know what it means, you might not. Notice here it's giving me the line number. Remember we turned on those line numbers a little bit ago? This is why that's important. As it's literally pointing to line 6, saying z equals a star star x. Name error. Name a is not defined. Oh, this is that thing we talked about earlier, that you can't use a variable that the computer doesn't know what it is. Just like I should not be using a word that you don't know the definition of. If I'm going to use a new word with you, I need to define what that word is. So what I have to do, I have to tell the computer what a is. I say, oh, okay, I'm going to go in here, and I'm going to say a equals 6, whatever a was supposed to be. I just forgot to include it. I do it all the time. I can probably count on one hand the number of times that a code has run perfectly the first time I wrote it. Then when I go back to run this, right, because you get unlimited tries, right? It's not like a chemistry lab where you're running out of hydrochloric acid and you only get a certain number of tries. You get infinite number of tries with a computer code. I'm going to click on run this cell. Now I get a printout. I get X, Y, and Z. And I don't get an error message. And that's really what you're looking for. You keep making adjustments based on the computer's feedback until you don't have any more error messages. It's just that simple. Step 7. So far, we haven't done anything with Python that we couldn't do with a graphing calculator, right? So I know what you're thinking so far is I can do all of that in my graphing calculator and it doesn't yell at me like that. Well, it does, right? It'll give you an error, but it doesn't give that many errors, right? Its error is one line, not a paragraph long. But one of the main advantages, sorry, pause for cough. But one of the main advantages that a programming language like Python offers is the ability to tell the computer to repeat a set of instructions. Here's what I want you to imagine, right? We're trying to model motion in a circle, right? We're trying to go all the way around the circle. Think about how many points you need to draw a good circle. 100, 500, 1,000? You need a lot of points to get a nice smooth circle. You're not going to get away with 5 or 6 points, right? That's definitely a pentagon or a hexagon that you're drawing. I want to be able to give these instructions to the computer and say, do this over and over and over again for a list of different values of t, right? I want to be able to tell it what the t values are, and I want to tell it, calculate cosine and sine for me of each value of t. I want it to repeat those instructions. That repetition is called a loop, right? You do one thing, you do it over and over again, you just keep looping. There's a few types of loop out there, and we're going to get to a couple of those in our class. But the one I'm most fond of is the while loop. A while loop is set up like this. You need 2 pieces. You need a condition, and you need the... Oops, excuse me, should not have double-clicked that. A while loop is made of 2 pieces. You need a condition, and you need the set of instructions for the computer to repeat. The condition is some kind of expression that you're asking for the code to check on. In a while loop, this might be something like while t is less than 7, meaning the code is going to repeat as long as t is less than 7. You might start with 0 and go to 1, 2, 3, 4, 5, 6, 7. Oh, 7 is not less than 7. I'm done. As soon as t is no longer less than 7, the loop is going to stop and the code will continue on to whatever it has next. The instructions to repeat are just more code that you specifically want it to repeat. How do you tell what are the instructions to repeat? Because they're indented. I want you to come down here and look at this. We're setting up a loop while t is less than 7. We're going to repeat these instructions. So there's 2 pieces to telling Python what you want to repeat. There's the while statement that needs a colon at the end. That colon is just code for there's a block of text coming. And then for everything you want it to repeat, you indent. You just press tab. And in fact, when you first type in this while loop, let me show you this. This is really cool. When you first type in this while loop, while t less than 7, colon, when I first press enter after this, Jupyter automatically indents for me. And so I can give my instructions here. And then when I'm done, I just backspace and I'm done. Now those are not going to run. I'm going to delete those because that's gibberish. But you get an idea of how easy it is to set up a loop. As long as the lines are indented, they are part of the loop. They're going to be repeated. So what do we have in this loop? Again, think about these things as being repeated. We have t equals t plus 1. This should give you some hesitation, right? Because you would never write this in a math class. What this is saying, this is not written the way it's written in a math class. Because in a math class, you would say, well, that can't possibly be any value of t. No number t is going to work there. What this is doing is saying, I want you to add 1 to t. Okay, t starts at 0. So 1 plus 0 gives me 1. I've calculated 1. What do you want me to do with that 1? Then you're telling the computer, I want you to set it equal to t. The computer says, no problem. I will forget what t used to be. Right? So t was originally 0 up here. It's going to forget what t used to be, and it's going to store 1 in t. Right? It's kind of like when you're writing a document and you save a new version of the file. You're overwriting what you had before. Then calculate x equals cosine t, y equals sine t, print t x y. That's where the indentation ends, so we loop back around. T equals t plus 1. Oh, I know what t is. T is 1. 1 plus 1 equals 2. What do you want me to do with that 2? I want you to store it as t. Okay, t equals 2 now. In the next loop, you can probably guess t is going to equal 3, and then t is going to equal 4, and then t is going to equal 5, and then t is going to equal 6, and then t is going to equal 7. Right? It's great because the computer's just going to keep going and repeating that. Basically what this line is saying is every time you go around the loop, increase t by 1. That's what that's saying. And then at the end, we're going to ask the computer to print for us the word done. Then when you run this, that's what you get. You get, let's take a look at this. We're printing t, x, y. So all the numbers on the left are t. We got t equals 1, 2, 3, 4, 5, 6, 7, just like we expected. When it comes back around to the loop, it says, oh no, t equals 7 now. So I can't repeat this anymore. So I am done. And then it comes out here to print done. You notice done only gets shown once, right? That's not part of the loop. See how it's not indented there? It's back up at the edge of the cell. That means it's not part of the loop. That's only going to happen after you're done with the loop, and it's only going to happen the one time. So that's pretty cool. I mean, think about if you had to do this in your graphing calculator. You probably have had to do this in your graphing calculator where you had the same calculation over and over again, and you press second entry, change the number, enter, second entry, change the number, enter, and you're just scribbling them all down. This is the way to get the computer to do that repetitious stuff for you. Then I'm going to ask you to modify the code to give us more data points. I'm asking you to either make the while loop repeat longer. So that means you change this 7 to a higher number, right? If I change that to a 17, it's going to give me a lot more numbers. It's going to go from 1 until 17. Pretty cool. Or I can make it increase t by a smaller amount each time. Right here, I'm increasing t by 1 each time. I could instead increase t by a half. Click run. Now you notice instead of going 1, 2, 3, 4, 5, 6, 7, I'm going 0.5, 1.0, 1.5, 2.0, 2.5, 3.0, 3.5, etc. You can make it smaller. You can make it 0.01. You're going to get more lines that way. The computer doesn't care. The computer is going to work all day for you without a problem. Step 8. The loop above produces correct results, but we don't usually read off numerical values, right? So if you hand this in as an assignment, it is technically correct, but it's not very helpful, right? We don't read off tables of numbers like this in physics usually. We usually prefer a graph. That's what this step 8 is for, is to help you learn how to create a graph in Python. We're going to use the matplotlib function. That's mathematical plotting library. I've got a link there if you want to go learn more about it. The way it's going to work, we import what we need from PyLab. Matplotlib is included in PyLab. We just have to tell it that we want Matplotlib to show us the results in line, meaning with all the printed stuff. You just have to include this little %matplotlib inline thing, and you don't worry about it. What's going to happen is we're going to create something called an array, right? In order to create a graph, I have to have a set of x values and a set of y values, right? What we're going to do, we're going to set up three different arrays. We're going to set up a time array that's going to hold my t values. We're going to set up an x array that's going to hold my x values. And we're going to set up a y array that's going to hold my y values. An array is just think of it as a list of numbers, right? What's going to happen is every time we go around the loop, here's our loop just like we had before, right? I haven't changed anything about that. What I've done is I've added to it this append function. You know what append means, right? That's where you have something and you want to add something onto it. So you're taking this array and you're adding another value to it. So in each go of the loop, I'm taking my new value of time, right? Because time increases every time we go around the loop. I'm appending that t to the t array. Then I'm taking my x value and I'm appending that x to the x array. Then I'm taking my y value, I'm appending that y to the y array. So my arrays are getting longer each time because I'm adding another number to them. Then we come down here and we have a couple of plot commands. Now, I have to re-look up every time how to set up these plot commands. So this is something you just copy and paste into your code, and then you make adjustments as you need to. So here I'm going to plot t array on the horizontal axis and x array on the vertical axis. So I'll have t and x. And when I run it, I get out this graph. It kind of looks like cosine, right? It starts at 1, goes down to -1, and then goes back up to 1. That's a really bad cosine graph. You would be pretty unhappy with that if you got it from your graphing calculator. The reason it looks so bad is because I'm only increasing t by 1 each time. Right? So my data points are spaced 1 unit apart. I'm going from 0 to 1 to 2 to 3, and Matplotlib is just filling in the rest with a straight line. Same thing with the y graph, right? So here I create a plot of y versus time. And I have to use these array values here because it's just saying, okay, here's a couple of array values. I want you to pair together the first points, the second points, the third points, the fourth points, the fifth points, etc. on down the list. Same thing happens with my y graph here, right? It's very jagged. We would not be happy with that if we were to turn that in. What you do, we need more data points, right? We need the data points to be closer together. So instead of increasing by 1 each time, I can just increase by 0.1 each time. So that's what I'm asking you to do, is make this into a smaller number. I'm not asking you to rewrite the code. I'm not asking you to create a new section or something. I'm just asking you to change that one number to something smaller. Then run it. Oh, look at those nice, smooth cosine and sine functions. Isn't that a lot better? Doesn't that look like the sine and cosine you know and love? Then I'm asking you to do one more thing. And I think I'll let you figure out how to do this rather than demonstrate it for you. I'm asking you to add some code, right? So far, all you've done is you've read code and run it and modified it. Now I'm asking you to add some code. I want you to add code that would create a graph of y versus x. I want you to come up here. I want you to use these as an example, right? I've shown you how to plot two different arrays, two different sets of data. I want you to think about what those two sets of data would have to be in order to get a graph of y versus x. Should be pretty straightforward. If not, just, what should I say there? That should be pretty straightforward. If not, just think logically about it. How did we create these graphs here of x versus time? How would you get one of y versus x? That's just what you have to think through there. Before you do that, though, I'm asking you, what shape do you expect to see if you're graphing a sine function versus a cosine function? What shape do you get? By the way, before you say it looks like an oval, add this little piece of code just before the show command that you need. That'll help you out there a little bit. And then I'm just asking you to add those descriptions there. Again, you double click inside here, you add your answers, press Control-Enter or the arrow button. And then down here, that's an extra credit step. I'll let you play around with that, figure out how to do that. Okay, so let's say you've spent the last half an hour making your answers to this code. You've probably done it faster than I have walking through it anyway. And you are ready to submit it, right? I don't see your Jupyter server, right? At least I don't think I can. I guess I could find out if I can. But I don't see your Jupyter server. You have to get this file to me somehow. The first thing you want to do is save in Checkpoint. I'm sure you've been saving along the way, like a dutiful programmer would. But what you do, you just click on File, come down here to Download As. This is how you download the file from your server to your own computer. Come down here and select this notebook format, right? It is a Jupyter notebook. So the best way to save it is as a .ipynb file. You can try out these other file formats if you want, but the one I'm looking for is .ipynb. So you click on that option. It will open up a little save dialog, and you just choose where to save it. Save it somewhere you can find it. Your downloads folder, your documents folder, your class folder, your desktop, wherever you want. It's your computer. So I'm going to save this assignment 01 from Brian Lane. One last chance to change the file name. And then I'm going to click save. It's going to save it just like as if I was downloading a file. It's just got a funny extension. And then what you can do, you can take that file that's now on your computer, upload it to Canvas, or email it to your instructor, however your instructor wants you to submit it. For my students, I'm asking you to submit it to the assignment posting on Canvas. And that's it. That's all you have to do to work through a Jupyter assignment. The only thing that changes is what you're asked to do during the code and during the write-up. So I hope that's helpful to you. I hope you can see how this is a wonderful way to communicate some physics research to other people. Thank you so much for watching. I will see you next time. Bye-bye.